World and Universe.
Okay.
Welcome to iCANX Talks. My name is Chi Zhang. I'm a professor from Beijing Institute of Nanoenergy and Nanosystem, Chinese Academy of Sciences. My research is focused on the microenergy devices and self-powered sensing. I'm very honored to be the moderator of this talk and discussion. Today, we are going to have the 119th talk. The speaker is Dr. Hamida Hallil Abbas from Bordeaux University. We also have three panelists for question and discussion today. So first, please allow me to introduce our distinguished speaker today. Dr. Hamida Hallil Abbas is an associate professor in electrical engineering at Bordeaux University and is affiliated with the IMS lab in France. Her research focuses on the design of innovative devices and sensors using electromagnetic and acoustic transduction modes. He has a background in microtechnologies and has developed experts in understanding the interaction mechanisms involving chemical and biological detection. From 2018, she spent 2 years as an adjunct research scientist at the School of EEE, NTU, and the Central Lab in Singapore, where her work centered on developing two-dimensional-based acoustic and microwave devices. She is also a member of the Academical Council. She has been an active member of the HV Sensor Council since 2018. Her research work and dedication to the sensor community has been recognized and rewarded through 20 invited talks, 5 Best Paper Awards, and additional recognition awards. Now, let's welcome Dr. Hamida to the stage and give her talk. Let's welcome.
Thank you, Professor Chizang, for this presentation, and greeting from France, especially from Bordeaux City. Before to start, I would like to sincerely thank Alice for this invitation, which honors me to contribute to the iCANX talks. So let me share my screen for my presentation, please. Could you see my screen? Everything is perfect. Thank you so much.
Yes.
So thank you. So today I am going to present an overview on future challenges and opportunities for electromagnetic and acoustic wave-based sensors in environmental and medical health. So before starting, I would first like to introduce the city where I work and conduct my research. It is the city of Bordeaux, located on the southwest of France. This city is above all rich in its culture and its gastronomic and architecture heritage. It is also economically dynamic in several fields, such as aeronautics, space defense, laser, pharma, ICT for health, emerging clusters such as energy and other creative industries. In this slide, you can see a part of our industrial patterns logo. So I am employed by the University of Bordeaux, the third largest French university. Based on the number of students, it has more than plus 56,000 students, and around 30% undergraduate, 23% postgraduate, and 30% health degree, and other also degrees. My research activities take place mainly in the EMS laboratory, which stands from the Laboratory for Integration from Material to System. My laboratory is supported by 3 primary administrative affiliations: my Bordeaux University, Bordeaux IMP, and the National Research Center, CNRS. The research area explored within my laboratory is presented here. So EMS offers a unique scientific positioning in systems engineering, the integration of hardware, intelligence, and knowledge in communicative and human-centered systems. So EMS supports fundamental research as well as project-based interdisciplinary research. More than 100 research grants are currently running in EMS, targeting domains such as transportation, telecommunication, health, environment, and energy. So therefore, my research activities are focused on societal challenges related to health and the environment. So the outline of my scientific presentation for today is as follows. First, why we need transducers. So then I will start by presenting resonance sensor principle and their interrogation, such as BO and flow devices, acoustic sensors in wireless configuration, electromagnetic radio frequency platforms, and their application, especially acoustic wave-based platform for chemical biosensing and physical parameter monitoring, and electromagnetic radio frequency platforms for the no-contact organic matter and chemical molecules monitoring. Then future challenges and opportunities will be given for a few examples and studies in application for monitoring and investigating disease process in vitro, exploring of potential of 2D materials in radio frequency piezoelectric acoustic wave devices. So indeed, our work is motivated by the different issues presented here as the need of in vitro tests for real-time and early disease, diagnostic, treatment, and therapeutic drug monitoring, and also real-time monitoring of surrounding physical quantities, detection of physical parameters. For example, if we need to use this kind of transducer in health effect of pollution so we need to detect few quantities, chemical or biological or physical, such as biomarkers, toxic gases, volatile organic compounds. However, at very low concentration, few ppb or nanogram per liters, and this can work on liquid or gas medium. However, the existing system today have many disadvantages, such as bulky and expensive, no generic platforms, indirect response, poor selectivity, ethical consideration, and energy consumption. For this, there is a need of introducing new smart technologies to bring ultra-sensitive and selectivity for these sensors, low energy consumption, portable and wireless, adapted to chemical and biosensing and preference. So as you can see in this scheme, we are showing a versatile sensing platforms. Gas or biosensor use a specific active layers, as you can see here, to capture chemical or biological target analysis. The active layer usually depends on the sensing application, gas or liquid, or just physical parameter sensing. In this case, sometimes we don't need this active layer, and we can use just the transducer, as you can see here. And here there is also a presentation of some principal application of transducers, such as acoustic and electromagnetic transduction based on different technologies. We can see surface and bulk wave acoustic platforms and electromagnetic radio frequency platforms here. But we will discuss them deeply on the next slide. So in the resonant transducer, we can find a family of sensors based on elastic waves, such as the BO, bulk acoustic wave, QCM, quartz crystal macrobalance, and film bulk acoustic resonator, and SMR solidary mountain resonator, and surface acoustic wave based on Rayleigh, Love, and film plane. So if you want to compare these platforms, please read this table that you can find on this article that we published in IEEE Sensors in 2021 in order to understand the comparison deeply of all of these technologies in terms of sensitivity, limitation, and key theoretical expression. For example, as you can see in this figure, a surface acoustic wave daily liner consists on an interdigital transducer on top of a piezoelectric substrate. If we excite the transducer with an electrical signal, we can generate a mechanical wave. And this wave perturbation will induce a phase velocity variation and an attenuation. If we coat a daily liner with a sensitive layer that is specific for certain molecules, the suction and the diffusion of those molecules and in the sensitive layer will induce an attenuation of the perturbated wave and consequently decrease the phase velocity. So we can detect the concentration of the target analyte. So this animation simulation of the generated log wave, so log is the mathematician who described this shear horizontal surface acoustic wave propagation. Thanks to the top guiding layer here, for example, silicon oxide, in our case, we can have an energy confinement and then high mass loading sensitivity. To achieve a clinical sensor able to work in liquid medium, so we need to gather this kind of platform with the biocompatible microfluidic chip. In this slide, we also reported the schemes of given in our article that I cited before for your reference to discuss the acoustic sensors in wireless configuration. Indeed, two configurations on interrogation are possible, and they are depending on these two geometries, as you can see here, the geometry of the resonator and the geometry of the reflective daily light. In addition to the acoustic platforms, we also studied deeply the electromagnetic radio frequency platforms, usually operating in direct and indirect microwave configuration. This given table discusses the design roles such as the geometry and the microwave frequencies to achieve at very high sensitive radio frequency. The synthetic overview of this comparison between all details in the reference given here also for understanding the theory and all geometries existing for this kind of microwave platform. So indeed, two examples were given here, the basic principle of micro resonator and the basic principle electromagnetic wireless LC resonator. So for the first example of microwave resonator is illustrated here. So how it's works, its principle. So the presence of molecular or physical parameters induces modification of physico-chemical properties and consequently modification of electrical properties of materials. So this variation induce perturbation of electromagnetic wave and then modification of microwave resonator response. For the electromagnetic wireless LC resonator, it is constituted of a flat bobine coil connected to a capacitive sensor, for example, a pressure sensor here, and deposited on a flexible substrate to constitute a wearable sensor. The LC resonator is remotely excited and read by radio frequency coil, as you can see here, coil tuned around the resonance frequency of the LC resonator. In the event of pressure, for example, change, the induced capacitance changes will result in a resonance frequency shift and the resonator which constitutes the output of the device, as you can see on this figure. After the presentation of the operating principle of the elastic and electromagnetic radio frequency was based to the transducer, let's talk about their application. Here, an example of using a love wave sensor associated with molecularly implanted polymers, MIP. For the real-time colorectal biomarker nucleoside was illustrated, as you can see here. So here is the test bench used to make these measurements. In this figure, we can see that this study, we succeeded to detect 5 ppm of the targeted biomarker, as you can see here, which shows the feasibility of real-time diagnostic tool for colorectal cancer. Another example here also, using acoustic transducer associated with the graphene oxide. As you can see here, we have made 4 platforms. And this experiment succeeded also in detection of few ppb of ammonia, as you can see here in this figure. Finally, another experiment was conducted in the harsh environment here, under 1000 degrees Celsius. So we can see here the shape of the SO electrode under this temperature. To sum up, elastic wave transducer offer a very high sensitivity. However, until now, an effort is conducted to offer selectivity and repeatability, and we have still bottleneck to find the right substrate combination with electrode, and also to secure its degradation, and also how in harsh environments we can avoid the issue of interdiffusion and the interconnect with the antenna and packaging in wireless configuration. We can also confirm the monitoring of fruit ripening, for example, with the wireless LC resonator. As you can see in the presented figure, so here we have the kiwi fruits. So thanks to the monitoring of the permittivity and conductivity during ripening, so you can see here in the figure, you can see shift of frequency that show versus days how we are following the ripening of this kiwi. In the figure, in this these 2 figures that you are seeing here for results, we are using microwave resonator to monitor in real time molecules such as pesticide, for example, and ethanol, which is a volatile organic compound. And we can see that we can monitor these target spaces in real time. However, as we show for the acoustic transducer, even the radio frequency transducer suffer from selectivity, repeatability, and reproducibility of measurements. So after providing an overview of the interest in transducers based on electromagnetic and mechanical wave for monitoring environmental and biological parameters, this section offers an overview of their application in monitoring and investigating disease processes in vitro. Specifically, our research is driven by significant concern related to heart and brain disorders, which are recognized as leading causes of human mortality. Cardiac disease rank highest among mortality factors, while neurological disorders are not only the second leading of mortality, but also the primary cause of disability. To study this disorder, there are many tools. These tools explore the properties of cells such as neurons and cardiomyocytes to obtain information about their behavior. These properties can be electrical, chemical, or mechanical. Today, there are several ways to measure cellular properties. Brain cells are generally characterized by their action potential, which have chemical, electrical, and mechanical properties. Indeed, during the propagation of the cellular potential along the cell membrane, an electrical potential as well as a mechanical deformation propagate at the same time, and there are chemical exchange with the extracellular medium. In case of carbon-mutate concentration, electrical potential and chemical exchanges are recorded. Carbon-mutate can actively regulate contractively the compensation to load changes at the single cell level. The recovered data is processed and then exploited. Some of the existing techniques include techniques, as you can see here, there is an overview of all existing techniques. So all these techniques recurring electrical signal using electrode or microelectrode, such as ECG, EEG, as illustrated on these figures. So ECG for electrocardiogram and EEG for electroencephalogram. Impedance measurement techniques such as also IIT or IIC also use it. Imaging techniques that you are seeing here, calcium or photoacoustic, for example, are the most popular indeed. So calcium imaging, which exploits the chemical properties of cells using markers sensitive to calcium. There are also other techniques like PET, so positron emission, tomography, AFM atomic force microscopy, but it's still under research. Here we are exploring also the mechanical and electrical behavior of neurons and cardiac cells. It is crucial to grasp these fundamentals as we ask important questions. Can we develop effective tests for screening disease in labs, and can we find alternatives to testing on animals? We face significant challenges, both biological and technical. Biologically, we need to understand how different cells like astrocytes, microglia, and fibroblasts grow and how temperature change affect them. Technically, we are examining how well current platforms perform. Could acoustic platforms be a solution? Indeed, acoustic platforms can be a solution, as this kind of transducer is already used for studying cell properties, behavior, manipulation, respiration, sieging, and proliferation. Some examples of platforms are given here, and geometries are developed in state-of-the-art for the studying as introduced before the cell properties, behavior. You can see all this in the state-of-the-art. We can find few work are beginning to study, for example, cell manipulation, separation, switching, migration profilation, and properties, and also behavior. And very recently, around 2015, so as you can see in the study of Dong et al. And also of Karesh, so studies started to report using of techniques exploring the mechanical properties of cells. This is the case of the device based on quartz crystal microbalance using bulk wave presented in 2019 and reported here. This study showed for the first time the growth of population of cells thanks to their changes in mass. So here you can see all the experiments in detail. Another publication presented also here, studying the behavior of population of cells exposed to drug delivery by measuring their viscoelasticity using guiding shear horizontal wave sensor. The results of this experiment carried out show a variation of the viscoelasticity according to the drug concentration, which suggests that this technology could eventually be useful and subject to having a good suitable cell model and conducting more tests. However, the measurements could not be carried out for a period longer than 9 days. So here we can see that there is limitation for the QCM, for example, platform, and 30 hours for the SUTIP platform. Moreover, about the state of cultured cell population remain unexplained or understood. So, what is the next? So I would share with you this analysis coming from two articles from authors Thierry Leichley, as you can see here, figure from this journal, and the second from Otto Warbach, that here mentioned some analysis. Indeed, these figures show how researchers, so here in this figure you can see, how researchers and promises sometimes are far from the reality. I mean the end user. For example, in biosensing, usually the researcher is asking this question: is the microfluidics working properly? Are my bioreceptors properly attached? However, from the other side, here the doctor is asking, can I trust the results? So, the author Warbach suggested this question that we should ask before to think for a project based on sensing for bioapplication. Will it be possible to monitor the evolution of the biochemical parameters over time? Will the sensor operate continuously for up to 12 hours, for example? Will it be responsible reversibly as a temperature, oxygen, or pH sensor? So we have many questions to ask before to design a chemical or biological sensor, but still we hope and dream to develop platforms based on multi-physics, as you can see here in starting on the state of the art, and multi-transducer approach. This is feasible thanks to the potential innovating geometries and powerful algorithms today that could help us in getting to selectivity. In this next part of our presentation, I will discuss the recent advances we have made in exploring the potential of 2D materials in radio frequency piezoelectric acoustic wave devices. So we have seen a rapid development of wireless telecommunication systems, and this can be attributed to the strong demand from the Internet of Things, 5G, and artificial intelligence. However, to satisfy these demands, there is a need of devices with advantages of higher operating frequency, lower insertion loss, higher integration capability. So why not flexible? Among these devices, radio frequency filters are most important components. To optimize like acoustic radio frequency filters, which can be classified in two surface acoustic wave sensor and bulk acoustic wave sensor filter. As presented before, for few devices, the acoustic wave travel on the surface of piezoelectric material, and the BOO acoustic device, the acoustic wave travel in the volume of the piezoelectric material. Compared to SU device, BOO device have several advantages. Firstly, smaller in size, and additionally, the operating frequency of SU resonator typically does not exceed 2.5 gigahertz, as you can see on this figure. A BOO device can operate at several gigahertz. These unique capabilities make BOO devices highly desirable for modern radio frequency applications. There are several possible configurations for BOO devices for radio frequency filtering. The first is known as Abbas, which is composed of a thin piezo layer. Two electrodes here, as you can see here, two electrodes and the air cavity. The thickness of the piezo layer is equal to half of wavelength at the resonant frequency. Another type in the SMR, which is, as you can see here, the geometry of the SMR, which is an F bar, but with an acoustic Bragg mirror. So acoustic Bragg mirror is here, has a thickness equal to 1/4 of a wavelength. Generally, they operate at thickness exponential mode with the longitudinal acoustic wave. However, SMR resonators are more robust compared to F-bar resonator, since the Bragg reflector can also serve as mechanical support. So here we can see for the F-bar, we have directly a membrane, but for the SMR, we saw it's hard, and we can see that the substrate will support that. This is why the design and the optimization of the SMR structure is for particular interest for using in 2D materials. So to conduct the design of the BOO devices, there are several important factors should take into account. As I mentioned before, the resonance frequency depends on the thickness of the piezoelectric material. So here you can see the thickness. So in the first important parameter, then the velocity of the acoustic wave in the second parameter to determine the resonance frequency. And it depends on C33 elastic constant, E33 piezoelectric constant, and epsilon33 dielectric constant. So let's discuss about the main challenges of the existing F-bar. From the principle of design theory, we can see that we search for the piezoelectric layers with high wave velocity, low thickness, and high coupling coefficient. However, limited by the current fabrication process, the current conventional piezoelectric materials cannot meet these three exigencies at the same time. So, what is more, the traditional fabrication process will lead some misoriented of crystalline structure at certain thickness or on certain substrate. Also, the roughness of the surface also increase when the layer is thicker. All these defects of conventional piezoelectric material with conventional fabrication process will lead the degradation of the wave propagation and then degrade the performance of the whole device. So how can we solve these problems? And we can make use of the exploring imaging novel materials. So let's talk about interest of 2D nano materials. So the discovery of low-dimensional materials has resulted in the emergence of many new research areas. One researcher succeeded in creating graphene, which is essentially graphite flakes with only one layer of carbon atom. By mechanical exfoliation, it quickly caught people's attention. In addition to graphene, there are other 2D materials, and we will focus on TMD family with a chemical formula of MX2, transition metal atom, and X, a halogen atom. So why we choose the TMD type? When comparing graphene and MOS2 of TMD family, for example, so MOS2 is predicted to be piezoelectric material. This property makes MOS2 a potential candidate for downstream acoustic devices. TMDs like MOS2 can have different prototypes depending on the staking order and atom coordination of MO atoms. MOS2 can form three crystalline structures, namely 1T, 2H, and 3R structure. The thickness of a single layer of MOS2 is about 0.7 nanometer. Research on the piezoelectric properties of 3-RMOS2 is usually based on molecular dynamic simulation using first principles density functional theory FDT, which led to the parameters that you can see here in this table that we find from the Konabi work. So on the figure, we see the work characterization here. So you can see on this figure or this figure of D33. So here we have the D33, which is by using the piezo, D33 as performed by using piezo response force microscopy by our French and Singaporean group. We can observe positive and negative also output voltage and current under periodic loading with increasing decreasing strain. This clearly indicates that mechanical deformation is being converted into electrical response in agreement with piezoelectric behavior. So if you need more information about this experiment that we conducted, so please read this article on this field. So the next, I will discuss the modeling and simulation of the 3-RMOS2 SMA. Now, based on this knowledge, we consider a 3-RMOS2 based SMA. We have designed it with a thickness of 100 nanometer. Why we choose 100 nanometer? Because for the exfoliation process, this was possible on the clean room. You can see the constructed model here on the figure. The thickness of the acoustic Bragg mirror layer is 1/4 wavelength. The substrate is of fused quartz, transparent for the easy process of fabrication that we made by NTU in Singapore. So these are the results of the electrical performance. From the impedance curve, the minimum is observed at 18.3 gigahertz, which is the resonance frequency, and the maximum is observed at 22.7 gigahertz, which is the anti-resonance frequency. Compared to the results of other 2D material, we have superuse models mainly depend on the elastic and piezoelectric properties of 3-RMOS2. So we calculated the electromechanical coupling coefficient, KT squared, to be around 47.8%, which suggests that 3-RMOS2 has a very high electromechanical coupling. On the right figure, for example, you can see the curve of the impedance phase. It performs a typical Bordeaux device phase change. Many superiors and sharp modes can also be observed. We also conducted an analysis of the mechanical performance of the device. On the left figure, you can see the displacement field here, thanks to the finite element simulation, which indicates the propagation of the longitudinal acoustic waves in each layer. By studying the mode shape shown in the right figure, we can see that main peaks of the mechanical performance are observed at the center of the SMR, which are vertically symmetric on the surface of the piezoelectric layer corresponding to the desired thickness extension, longitudinal mode here. Now, we will talk about the geometry design, because we need to design this device on the radio frequency for characterization after. Apart from the desired longitudinal acoustic waves, some lateral acoustic modes can also propagate in both devices. These spurious modes appear in the electrical response of the resonator as parasitic resonance that superimpose on the target resonance. To mitigate this degradation caused by undesirable lateral modes, apodization is the most common method used. As shown on these two Smith chart, The irregular electrodes show much less superior mode. Pentagons, so the form of pentagons here, are the most commonly used shape for the electrode and where we will also use into our design, as you can see here. Sorry, just here is the 3D illustration of the design 3RMOS2, as you can see here. The Bragg mirror is the structure that we designed for 100 nanometer. However, to obtain accurate electrical characterization, it is crucial to consider also switchable electrical connection within the entire design. So here, because we should arrive by our measurements on the top, and also we should touch the ground. We add, this includes having matched access to 50 ohm for the operation at gigahertz frequencies, as well as having paths that are compatible with commercial ground signal ground. So as you can hear, this is some rules for designing in radio frequency. Given size of our device, we have selected a probe with a pitch size of 150 micrometers. We have completed a dimensional design using IDS line calc function with coplanar waveguide. So here we use the coplanar waveguide, and you can see that we designed the transmission link that is matched with our design, and we can got adaptation of impedance 50 ohm at millimetric frequencies. Then finally, we are going to talk about the fabrication and characterization results after the simulation done and all the design part. So the main fabrication process includes deposition of acoustic Bragg mirror, silicon dioxide, passivation layer, aluminum bottom electrode, then the transfer of 3RMOS2 flax to load by deposition of pentagonal aluminum top electrode and titanium aluminum coplanar waveguide. After this process, finally we could get some prototype. This is an SEM images of a device zoomed in our SMR parts. We can see that the transferred 3RMOS2 flat has an irregular shape, but the layered structure and the mechanical exfoliation process ensure flat surface. We can clearly see also pentagonal top electrode as well aligned signal and ground zone here. You can see everything on this part. Because of its special transfer process, the thickness cannot be controlled with a high precision. And the final thickness of 3RMOS2 layer is between 202 nanometers and 290 nanometers. Here you can see the optical images of the top view of the whole device. The deposition aluminum waveguide show a good homogeneity. And SEM also here characterization performed on the cross section of the acoustic Bragg mirror. We can clearly see that silicon dioxide and tungsten layers are alternatively deposited on the substrate. The thickness control is good, and each kind of layers has nearly the same thickness. Here we can see finally the experiment S11 here, scattering parameters for 5 samples. So here we characterize scattering S11 parameters versus frequency. All 5 devices demonstrated clear resonance characteristic, and all the resonance frequency is higher than 20 gigahertz. So we are on the millimetric frequencies. The apparent difference in the 5 curves, so we are not on the same resonance, is because of the difference between the thickness of all the transferred 3 RMOS2, which is in exploration not precise. And you have also here the measurements of the impedance versus frequency. So here we selected also simple 4 for a deeper analysis as exhibits. So sorry, just to show you the simple 4. So simple 4 is the one in green. So that one, we selected this simple for deeper analysis as it exhibits a strong resonance on the impedance curve and the regular scattering 1-1 curve. The electrical impedance minimum is above observed at 25 gigahertz here, with nearly 50 ohm and the maximum of 33 gigahertz. So the coupling coefficient CATI square is calculated to be 47.6 as we find it on our simulation. This figure displays the resonance frequency versus thickness. So our results highlights that the resonance frequency is almost inversely proportional to the thickness of the 3 RMOS2 flags, which agrees with the theoretical analysis. The slope of this curve correspond to the half of the longitudinal acoustic wave velocity, leading to the wave velocity, as you can see here calculated, about 10.5 kilometers per second. So this promising advanced proposal presented here show a bright future for technologies dedicated to the field of telecommunication and real-time wearable sensing. However, it is also essential to note that these 2D materials are still under study as their area of uncertainty because of the process that we are using for its transfer, so such as installation. And particularly, this will cause the difficulty to understand the physical mechanism and the processing technique of their machine that need further exploration. As we conclude, so I am arriving to the conclusion. So let's look at the future and the potential possibilities ahead and direction followed by our community. So I would like to share with you today this concept from the United Nations. So global e-waste. It seems that global e-waste monitor for 2020, the world generated 53.6 million metric tons of electronic waste. In 2019, marking a 21% increase in just 5 years. The report predicts that global e-waste, including products discarded with electrical plugs, will reach 74 million metric tons by 2030. So I think that it is also good to make progress in 5G, 6G, in all new technologies. However, I think it's very important to use also to try to make progress in biosourced materials that are paving the way for environmentally friendly semiconductor components and innovative sensors that minimize environmental impact through biodegradability. In terms of sustainable manufacturing also, we are committed to adopting green practice in the production of the semiconductor devices and sensors, significantly reducing our ecological footprint. We are also focusing on energy efficiency by reducing power consumption. We are supporting eco-friendly technology solutions that benefit both our industry and the planet. So lastly, it is also important to work sustainable algorithm that aims to optimize algorithmic process, cutting down data processing consumption. So that's it. So thank you for your attention. And before to close, I would like to acknowledge here all organizing that funded our work here, as you can see. So thanks to their support. So I would like to thank my University of Bordeaux, my region, Nouvelle-Aquitaine, CNRS, ANR Agency of French, Union European, and also the Embassy of France and Singapore and NRF Agency in Singapore, and also NTU to fund all of this research. And all of this work was possible thanks to all the collaboration between my lab and all these French and international laboratories. So thank you very much for your attention. Thank you.
Thank you. Thank Dr. Hamida for your talk. And time is well controlled. The surface acoustic wave sensor is a typical MEMS device. And I see some new materials, new structure, and new application in your work. Very wonderful work. I think our three panelists will also have great interest. And now, Hamida, can you stop the share?
Okay. Yeah. Thank you.
Okay, now please allow me to introduce the first panelist, Dr. Hongjie Hu. Dr. Hongjie Hu is an assistant professor in the School of Integrated Circuits at Peking University. He received his PhD in materials science and engineering from University of California, San Diego, and carried out postdoc research. His research is dedicated to the development of wearable ultrasonic devices and stretchable three-dimensional stretchable electronics, aiming to achieve continuous and long-term monitoring and the imaging of human vital signs, deep tissue, and central organs. By utilizing materials science, advanced manufacturing, and biomedicine, his research aims to provide new solutions for human health management and clinical diagnosis and treatment. And welcome, Hongjie Hu. And the second panelist is Professor Jiaming Chen. Jiaming Chen received the bachelor degree in electronic science and technology from the Huazhong University of Science and Technology, Wuhan in China. He received the bachelor degree and the PhD degree from the University of Tsukuba in Japan, majoring in material science and engineering. During his PhD study, he had been selected as Japan Society for the Promotion of Science Fellowship Researcher. He worked as a postdoctoral researcher in NIMS to develop high-performance spintronic materials and devices in 2018. Currently, he's a full professor with the State P Laboratory of Transducer Technology, Aerospace Information Research Institute, Chinese Academy of Sciences. His research interests include magnetic sensor, spintronic materials and their devices, novel sensing materials, and MEMS sensor. And welcome, Professor Chen. The third one is Professor Zhuoqing Yang. Zhuo Jingyang received a PhD degree in microelectronics and solid-state electronics from Shanghai Jiaotong University in China. He was a JSPS postdoc fellow of the National Institute of Advanced Industrial Science and Technology, Tsukuba, in Japan. He is currently a full professor in the School of Electronic Information and Electrical Engineering in Shanghai Jiaotong University. His research work mainly includes MEMS initial switch, power MEMS, nano energy packaging, and three-dimension MEMS integrated manufacturing technology. In the recent years, he has published over 100 academic papers, and he has served as the session chairs of many international conferences. He has selected into the Shanghai Pujiang Talent Program and won the first prize of technology invention in Shanghai. And now he's a senior member of IEEE. And welcome, Professor Yang. Now, let's welcome three panelists to the stage. Okay, well done. Okay, Dr. Hongjie Hu, you can ask first if you have a question.
Okay, thank you for Professor Zhang's introduction, and hello Hamida, a very nice talk. And I have some questions about your work. The first one is about the SAW, the surface acoustic wave. I noticed that most of those applications that can be used for using the SAW is in vitro, which means you always use SAW to on cell scale, right? I'm curious if we can use SAW on human skin or on human body to sense some, for example, some properties of human body or human skin. Yeah, can we directly put the SAW device on human skin and sensing? Yeah.
Yeah, thank you, Professor Hongjie Yu, for this question. I think the issue today with SAW are not biocompatible, the materials that we are using. So as you can see, for example, mainly we are using for piezoelectric quartz, or we are using natural gallium or ZNO. So today they are not biocompatible, but in case that we can imagine that we can protect them with some biodegradable materials, so then bioadapted materials, so then maybe we can use it for that. And as I finished my talk also, Professor Hongjie, I was speaking about biodegradable materials and sustainable technologies. So I hope that because research could go on that direction, that we can maybe we find the new properties of piezoelectricity in this kind of bio materials. So then from that, we can imagine, as we see it for 3RMOS2, we can imagine a new design that we can adapt that is more adaptable for, biocompatible.
Understand. Yes, biocompatible is a very important point, right? And I know in those traditional ultrasound field, people always use KNN, which is a kind of biocompatible material for those implantable ultrasound sensor for making. I'm not sure if the material KNN can be used to generate the surface acoustic wave.
I think today it's very difficult. There is this issue of biocompatible of materials, but also there is another issue is that the SAW is so sensitive also. So it's today we have the issue, as I show at the end of the application of SAW devices. The issue today is the selectivity also. So selectivity is a big issue. If we make our SAW sensor also on the skin, So it will be very sensitive for humidity that we are delivering on the sweat of our skin because of the changing of temperature. So there is today some direction that we are using, for example, artificial intelligence thanks to the progress in algorithm, in order maybe to make multi-transducer, and then thanks to this progress, maybe we can also, reduce all of these parasitic parameters around the measure that you on the skin. Why today is difficult really to see a positive issue of so directly adapted for monitoring from the skin. It is from my point of view.
Okay, thank you, Hamida. Thank you for your answer.
You are welcome.
Okay, thank you, Professor Hu, and Professor Jiamin Chen.
Oh, hello. Hi, Professor Hamida.
Hi.
Yeah, thank you very much for your very wonderful and very detailed presentation about the electromagnetic and acoustic ray-based sensor. And so I'm not so familiar with this field, but I have a few questions that I want to discuss with you. So the first one is, I remember that in your presentation, maybe in page 18, so you are talking about the high temperature endurance of the source sensor. It's about 1000 Celsius degrees. So I'm wondering that is that kind of sensor using the silicon substrate?
Yes. So this work is done by my colleague. I didn't, as I acknowledgement at the end. It's very, we have a team here in France, and they are in Nancy. They are working for the big, in big corrosive environment for big, manufacturing of metal and all of that. So for making measurement on this kind of placement, so is very interesting, because wireless measurement is you can directly operate by distance and got the measurement by distance. However, as you said, Jamie, this is really research. They are facing issues. Today, they got some measurement at 650, but they are not using parts. They are using, for example, substrate like langazite.
Yeah, so
there is other materials. It's not silicon, Jamie. It's not silicon. They are using langazite. It's another kind of material that you can increase temperature. Because, for example, quartz, if you increase temperature more, I think, than 350 or 400 or 500, you will miss the piezoelectricity. You change, you change the operation of the substrate. So you cannot get piezoelectricity. So they are using langazite.
Okay. So in that case, so that means the silicon substrate is not the good choice for the high temperatures sensor, right?
Yes.
So, for example, have you ever tried like the material like the aluminum oxides for that kind of sensor substrate? Maybe that kind of material can embase much higher temperature, right?
Okay, and is this material is also piezoelectric?
B2, I'm not so sure, but maybe we can check later. Yeah.
Yes, because it's very important that this material should be piezoelectric, and crystallinity is very important, because, for example, in my talk, I was speaking about 3RMOS2. Why, for example, we cannot use the RMOS2 that we can make by PCVD method? It's impossible, because crystallinity is not good as the one that you have directly from exfoliation. So it's very important to respect this in order to get the electrochemical, coupling between the design and to make it for radio frequency working.
Okay.
But yes, Jamie, I am really, I am please, we will exchange after by email to get this material and to see. Thank you.
Yeah. So thank you. And another question is, I remember that you talk about the molybdenum disurface material, right? Using that kind of material for the soft sensor. And normally when we fabricate this kind of 2D material, so actually it's a kind of flake trace, right? So is the size of this trace also affect the device property?
Yes, because as I show, I don't know if I can again share my screen. Is it possible? Is it possible to show just maybe? No? Is it no? No possible to Professor Cheese? Possible to share
Maybe
my
we should ask the chairman.
Yeah, I don't know. But anyway, let me try to explain.
Okay.
So, you know, for using 2D materials here, we didn't use surface acoustic wave. We use bulk acoustic wave. Why? Because we are working on volume, because we cannot use 2D for big surfaces as we need for two devices. Okay? So we use small surfaces. And why we make both surface, bulk acoustic wave, no surface acoustic wave. And because it's very important, the thickness of this kind of material is very interesting because, you know, today, for example, in existing filters in telecommunication, they cannot increase the frequency because you know, zinc oxide and all of this existing piezo material, we cannot reduce the size because the wavelength is dependent on the thickness of your material. So why 2D materials are very interesting for this kind of application. You see why? So why we use the thin, but very important that the crystallinity should be there in order to be sure that the wave will propagate within this,
Okay. So that means that the thickness of the material is much more important than the surface
yes,
of the material, the surface size of the material, right? For your devices.
Yeah, but also surface is important. Otherwise, you will not deposit properly your metal. You know, we need also the deposition of the metal on the top. So if we make air, for example, air gap between the metal ends, then the connection is not good. The wave, when you come to polarize your material, so then your material, because you will got some gap, you know, because imagine that your surface is something that, and you come to deposit your metal on the top. So you will got some air and your polarization will not be efficient. So also the surface is important, but in case of 2D material, what is nice is the surface is really flat, you know? So this is advantage also.
I see. So the last question is about the biosensor. So in your talk, you mentioned that soft sensor can be used for the biosensor, right? So I'm curious about the how is the biocompatibility of this kind of devices if you really want to use this for I mean in human body or in animal. For animal.
Yeah. Yes.
Like that.
So sorry for maybe I was not clear in my presentation. We can use biosensors, so as biosensor, but you use it like platform, no in the human, you know. For example, we have biomarkers in urine, sweat. For example, you take your sample of urine that have inside biomarkers of some disease. So then, thanks to this liquid, but we should also associate, as I said in my talk, a microfluidic chip in your soap, and then you control your liquid, you put it on, so you can use so device as biosensor. In this case, you can use it.
Okay, so basically it's uses like the platform, something like the in vitro way, right?
Yes. Today is really used like you know, QCM, quartz QCM for mass effect. It is used like that, like for mass effect like QCM. Yes, this is possible.
Okay, thank you very much.
You are welcome.
Yeah.
Thank you.
Okay, thank you, for the questions from Professor Chen. And Zhou Qin, please.
Okay. Okay. Thank you very much for Professor Hamida, Abbas, for your very, very interesting and very many aspects about the sensors. Very wonderful presentation. Okay, I have some questions to discuss with you. And in your presentation, you talk about use the magnetic radio frequency to measure in body visual, and because in many in body, it's the environment is very difficult, and such as the acid or alkylic, and is very not good for the measurement. And how to what do you think is the challenges in this measurement theory, and some impact will how to impact the frequency measurement distance between from the out of the body between in the body.
Sorry, the last one. Sorry, please say again for the last one. The first, I understand the first question. The second, please. Sorry again. Sorry, to be sure that I understand it.
What is the challenge in use this magnetic radio frequency to measure in a body visual, and some factors will affect the measurement distance between the surface and in the visual body. How to affect this?
Yeah, understand your question. Thank you for this. I think your question is I can answer for a question in two ways. I think the first way is the same, the response that I gave for Professor Hu. So sorry for my pronunciation. I hope that I do my best. It's the same, it's like acoustic wave sensor. All transducers today, they suffer from selectivity. If you are speaking about body, about a human body, the issue or surrounding parameters will affect the sensor. Especially, for example, for electromagnetic sensors today, what is the issue? The electromagnetic is more sensitive for electrical parameters, which are dielectric permittivity and conductivity. So the issue is that, that the permittivity of air is about 1. The permittivity of water is about 8. If we are on the body, so we know that the skin, for example, the issue is that if there is small changes, it's difficult to see them comparing to 8. The permittivity is so high, the permittivity of water. So yes. The selectivity is today the big issue of all of these kind of sensing, because we are speaking about chemical surrounding components. So what is the direction today from the community of sensors? So everyone, we are trying to use different transducers, multi-physical transducers. And thanks to the progress made by in algorithm data processing. So today there is this very nice advancement. So this is help if we have data from different, so then we can train our algorithm and we can calibrate sensors. So then we can deduce the effect of parasitic around these sensors. This is in this kind. But also there is another thing that is very interesting in radio frequency sensors and also acoustic, that autonomy in energy. Because other sensors, we need to use battery active things to polarize them, because working like diode, like transistor, or if resistive, so we need to convert it. But the advantage of these sensors, so imagine that you put this sensor on the body. So what is nice, you can make interrogation. You can polarize them by radar, for example. Directly, you polarize them by radar. and you send your power and on the right frequency of your sensor that is working. And the mismatching of your impedance will give the shift and the measure by distance. So this is the advantage of this kind of sensors. But today is still under research, that there is a big direction in this way.
Yes, this is not easy.
No, easy. No.
And you use the SAW to measure the cell or bio materials, and now you use the SAW is fabricated on the stiffness substrate, and maybe also you need to the flexible, and how to solve these problems in the future.
Yeah, this is, thank you for this question. Because we see today it's very important also to go in direction of flexible to make more easy integration of all this. So what is nice with 2D material, what is nice in 2D materials, we write it in our why we move forward for 2D materials with the team of Singapore. It's important to mention here this work was done between the French and Singaporean team. We were together because in Singapore, when I worked there, I understand that it was very important to go for this flexible, And you know why we went to 2D? What is advantage by 2D? Because we can explore 2D on a flexible substrate.
Yeah, maybe the package is also important.
Yes, this is yes. So on flexible, very important. So, but today, for example, when we are using crystals like ZNO or all of these, we cannot use flexible substrate in in conventional piezo materials.
Yes.
So
I notice you use the transform to.
Yes, but 2D materials could offer this opportunity to move for flexible components.
Yes. Because between the 2D materials, between the electrode, you also use the electrode, use the metals, and in my researchers and my students also find the 2D material between the 2D material with the metal electrode, the connect, the resistance is not very stability, and maybe you also use the annealing, but how to control the annealing, the conditions is very important.
Yes, I totally agree. Was what on my response for GM Chen. So when he asked me about, I said no, there is no just this, because when you deposit your metal on your material, so there is some gap of air, and then this is very it's an issue for the polarization and to be very close to your material, as your material is flux. We have a flux of 2D.
Yeah, the temperature is also very low.
Yes, you're right. Yep.
Yeah, maybe we also use the higher temperature is better, but it's not allowed.
Yes.
Yes. Okay. Thank you for your very kind.
Thank you for
Thank you for the question from Zhou Qingyang. And Dr. Hamida, so we have some time, so I have also some 3 small questions.
Please.
The first one, I'm curious about the power supply method for your device and the power consumption of the SAW device.
Yeah. So I didn't start by explaining that SAW devices and electromagnetic, they are passive. This is the advantages. They are working like filter. Filter, a radio frequency, we are not in DC. You have diode. In electronic, we have passive and active devices. Yeah. So resistance, capacitance, and inductance are passive devices. So SAW devices is not a transistor, is not a diode active. So SAW devices is like a mix of these passive. So we are not consuming energy, but we give power from outside to this to make the measurement. So when we make power on, it's outside. So we are not conforming to the issue of battery directly, but the energy that's coming outside, it's around, we are speaking about microwatt, I guess, about microwatt, just to excite it, and that you have directly the information from your vector network analyzer if you are making your connection, or from reader, for example, you can read it outside. Why if there is advantages for using this kind of devices? Because they are passive and they don't need battery directly. The power comes from outside.
So from the outside, from external power supply.
Yes, yes.
Milliwatt. Yeah.
Yes.
Okay.
Yes.
I know it. The second question is that by the end of your presentation, you have mentioned the environment friendly about the future device, and Professor Zhuo Xingyang has also asked curious the application in the body. Okay, so what about the body, the materials and the device can be degradable and the body friendly?
So this is, I finished my talk. Thank you. But this is a difficult question, difficult for a question, but I will try to answer, because I put it like perspective, because if I had an answer today, I will be happy to answer directly. So it's something that, it's a direction of our community. We want to go, I think, all of us, we know about the issue of e-waste that we are doing by our devices today. All of us, we know that clean room is consuming. All of us, we know that a clean room in consumption is the highest, place that consume energy. Also our e-waste that we know when we make electronic, and then we are not fixing the issue of electronic. We use a new, there is a new smartphone, and we are using all of this electronic. The issue today is that we are generating e-waste. Okay, so the good way, this is a dream, what I share with you. It's something coming from the UN Global World. So they said that it's very important that in electronics we should go on the direction that to find solution with chemists, that we can measure new properties of other materials that should be biodegradable. Not just for surface acoustic devices or all of that, or semiconductor, all MEMS, because we cannot, consuming energy like that, what we are doing today. So it's very important maybe to find the optimized process in clean room, to find the substrate, biodegradable substrate. There is new chemical materials are coming now, and we need to characterize them and to see their best for using for not just for human, for even for everything, because consumption that we are for the planet is so huge. So we need to, our footprint, environmental footprint should be a little bit more thinking. You see what I mean? I don't know if I answered to your question, but it's more philosophical question, It's this, yes.
Thank you.
You are welcome.
Okay, the last one that now the two-dimensional materials. Well, two-dimensional materials is widely researched, and you have also used MOS2 in your sensors. And so, what's your outlook of the integration of the two-dimensional materials to the MEMS, and what's the opportunity and the challenge for the future sensors?
Yeah, so thank you for this question. I think 2D materials are very, very promising. but there is a big challenge on the methodology of their transfer and the repeatability. Because today we are using exfoliation, so we can make 2 devices, 3 devices are close. However, we cannot, as we are doing with other materials, to be sure about thickness between this device and other device. So this is the first issue. So the repeatability of measurements. The second issue is also the fragility of the 2D materials. You know, they are a little bit as they are flex, so they stack and there is air between. And then there is another issue by using this kind of materials. So this is the second. So today so there is using of some exfoliation, automatic exfoliation method that they are trying to do that, but to be sure that we are using the same parameters for exfoliation of the 2D material and report it on the device. So there is a very nice progress on also. And the second one also is the physics around 2D materials. So today, so there is a very nice also progress because, you know, as 2D material is so new comparing to silicon. So we need to understand what is the physics surrounding and properties deeply. Because, for example, for us, when we use 3RMOS2, we find that properties that finally were given by simulation were not close to the experimental one. Because there is losses, there is other things. I think research is going on that, in that sense.
Thank you, thank you. Thank you, your answer in detail. Okay. The time is almost up, and now today we have a great talk from Dr. Hamida, and we also have a wonderful discussion from Professor Hongjie Hu, Jiamin Chen, and Zhuoxin Yang. And thank you all of you again. And especially thank you for the speaker, Dr. Hamida. And we also have a certificate for you from iCANX talks. Thank you for your wonderful talk.
Thank you so much. Thank you. Thank you. Thank you for all of your questions and for this really nice panel. Thank you.
Okay.
Thank you.
Okay, now finally, I will use 1 or 2 minutes to introduce the upcoming meeting in the next month. It is the iCANX Davos Summit. The iCANX Davos Summit will be held on July 11 to 12, 2024 in Davos, Swiss. This summit will invite the world-leading figures in related fields to share their latest achievements, thoughts, and leadership in innovation, science, technology, investment, management, and entrepreneurship. So it's called It's Time for Short. And welcome your attention to the Davos Summit. So now we will going to finish today's talk, and we in the next Friday we will have the next iCANX talks, and Professor Yihui Zhang from Tsinghua University will give his talk about the electronic spin, and welcome your attention. Please focus on the iCANX talks in the next Friday, and thank you for your attention.
Thank you.
Okay.
Thank you.
ladies and gentlemen, my dear friends, welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, and entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us. And it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
汽车电子化的迅猛发展，正在掀起一场技术革新的浪潮。